Just to bring you back up to speed with the titrations, we use a burette, and usually the titrations you probably have used a visual indicator. If it's a weak acid strong base titration, which is probably what you did in Chem 101, the indicator is phenolphthalein, so that's great because it turns pink under slightly basic conditions. We have a very important term in titrations called the equivalence point. As the name suggests, equivalent, that's when the amount of acid and the amount of base that you're adding are equivalent. So when the equivalence point is reached, the moles of the titrant and the moles of the stuff in the beaker are the same. So if I have base in the titrant, my moles of base, and if I have acid in the Erlenmeyer flask, that's when my moles of base and my moles of acid would be the same. Tomorrow in the lab, you'll have a strong acid and a weak acid in here, and you'll be titrating it with a strong base. And the equivalence point is when those two have the same number of moles. Now, there is an equation that we can use at the equivalence point. It is essentially our dilutions formula. So this is a really important equation. I call it the equivalence point equation. So to determine the volume of titrant needed at the equivalence point, we use MAVA equals MBVB. Meaning, let's say, if I have my titration, here's my burette, here's my Erlenmeyer flask. If I know my concentration of the acid and the volume of the acid in here, and if I know the concentration of the base, well, then I can plug in MA, VA, and MB, and I can solve for the volume of the base needed to reach the equivalence point. So this formula is incredibly handy. Okay, essentially what this formula is saying is the exact meaning of the equivalence point. If you remember, molarity is moles per volume. So if I multiply both sides by volume, molarity times volume is moles. Essentially what this formula is saying is the moles of the acid has to equal the moles of the base, and that's what it means to be at the equivalence point. So that's why this formula works. Now this looks like that dilutions formula from Chem 101, which is M1V1 equals M2V2. So it looks a lot like that. But this is we're going to need this equation quite a bit. This is how you predict the volume of titrant needed to reach the equivalence point. Now, maybe your titrant's an acid and you solve for VA, but you get the point. MAVA equals MBVB. Equivalence point formula. Very important. What you probably did not get in Chem 101 were titration curves. So this is what we're going to work on tonight, and this is what you're going to produce tomorrow. A titration curve plots pH versus volume of the titrant. This top graph, we would have a acid in the Erlenmeyer flask because we're starting at an acidic pH. So we got our pH probe in here, we got an acid in here, and we're going to add sodium hydroxide from the burette. Okay, and what's going to happen? Well, the pH is slowly going to climb, and then it starts to rapidly climb, right? It becomes asymptotic, and then it starts to level off again. Where on a graph, a titration curve, a pH curve, on a graph of pH versus volume of titrant added, where the concavity of the graph changes. If you're a calculus person, right, it's where the first derivative is 0, right, or whatever. Okay, so where this graph goes from being concave up to concave down, right there at that inflection point, to steal a term from math. Okay, that is the equivalence point. So the equivalence point always occurs at an inflection point. Now you could obviously run a titration in the opposite direction. We could start with a base in here. So we could start with a basic pH and we could titrate it with an acid. So we could have an acid in here. And again, where it changes concavity at the inflection point, that's my equivalence point. Now, there's going to be 3 types of titrations. So strong acid, strong base titration, strong acid, weak base titration, and weak acid, strong base titration. Those will be the ones that we're going to be doing, and we'll talk about the equivalence point at each one of those. They all have a different equivalence point. Cool. First, we're going to start with strong acid, strong base titration. Okay, so we're going to titrate hydrochloric acid with sodium hydroxide. to make water and sodium chloride. Okay, so let's titrate 25 milliliters of a 0.1 molar hydrochloric acid with a 0.1 molar sodium hydroxide solution. And let's calculate the pH along the way. So if you give me a second, I'm going to copy this down. So I just like to draw a picture when I'm doing my titrations. We are starting with 25 milliliters of 0.1 molar hydrochloric acid, and we're going to add 0.1 molar sodium hydroxide. So this is a strong acid, strong base titration, and I'm going to write the neutralization reaction for this over here. So HCl plus NaOH goes to NaCl plus H2O. So we're going to write that out. My first question is, what volume of the titrant do I have to add to reach the equivalence point? So where is the equivalence point? Okay, well, to get that, the equivalence point is going to be found by doing MAVA equals MBVB. So now this one's kind of silly because the acid and the base have the same concentration. They'll be at the same volume, but play along. They're not always going to have the same concentration. So 0.100 molar times 25 mils. You do not have to convert the volume to liters here as long as you realize you're going to get a volume out in milliliters. So if I plug a volume into milliliters, I'm solving for the other volume, it'll just come out in milliliters. You don't have to turn it into liters. So what volume of the base, if it's 0.1 molar, would be needed to react with 0.1 molar, 25 mils of 0.1 molar of the acid? Obviously, we divide by 0.100 molar. Those will cancel out since they're the same. And the equivalence point is going to happen after we've added 25 milliliters of the titrant. So 25 milliliters of titrant. So I want to calculate the pH at a couple places. The first thing I want to do is I want to get the pH initially, so before we add any titrant. So I stick a pH probe in here. I want to read the pH. So what is the initial pH? That's my first question. And this is really, really, really easy because this is a strong acid. Because this is a strong acid and strong acids fully dissociate, that HCl breaks up into H plus and Cl minus. That is the H plus ion concentration, right? So the initial pH is just simply the negative log of the initial concentration. So that's 1.00, right? So if we plug that in, negative log of 0.1 is 1. We got 3 sig figs on that, 0.100. So we're going to go 3 places past the decimal, which is why I went all the way out there. So this solution, if we were going to make a acid base, if we were going to make a pH curve of this titration, we are starting at a pH of 1. So, when I've added 0 titrant, we are starting with a pH of 1. And now what I want to do is I want to add some sodium hydroxide. I want to add some sodium hydroxide at various points before I reach the equivalence point, at the equivalence point, and maybe a point or two after the equivalence point. I want to calculate the pH. Okay, so the equivalence point is going to happen after I've added 25 mils of titrant. So let's just add maybe 5 mils of titrant. So the next question I have, call this question B. What is the pH after 5 mils of the 0.1 molar sodium hydroxide is added? What is that pH going to be? Okay, so how do we get that? What we need to do is essentially make a BAA table because we are adding something to this. So again, just like in the buffer problems, when we add something to the buffer, we do it with a BAA table. So we're going to do BAA and remember, BAA tables, everything has to be in moles. So we need to get moles of the acid that are in here. So 0.100 moles of HCl per 1 liter times 0.02500 liters. We're going to figure out how many moles of the acid we start with. That's going to be 0.00250 moles of acid. So before we add anything, this is 0.00250. We haven't added any sodium hydroxide, so no sodium chloride has been made, and the water is a pure liquid. So we just kind of leave it out because it's not part of anything we do. So now we need to figure out how many moles of the sodium hydroxide have been added. So that first A stands for addition. What are we adding? So we need to take the concentration of sodium hydroxide times that volume in liters. So we'll do it over here. 0.100 moles per 1 liter times 0.00500 liters. So we're adding 0.00050 moles, I believe, right? Let me plug that in. 0.1 times 0.005, 5 times 10 to the negative fourth, or 0.000500, right? So now I have more than enough acid in here to react with that base. So there will be no base left. This is going to consume that, so we need to subtract. This is going to go down to 0.00200 moles. And I will have made 0.000500 moles of sodium chloride. Now, here's the good news. In a strong acid, strong base titration, when you mix a strong acid with a strong base, you make a neutral salt. Confirm that in your mind. Sodium chloride is a neutral salt. Since it's a neutral salt, you don't have to worry about it. Now, when we get to a weak, strong titration, the salt is not neutral, and then you got to worry about it. Okay? So strong acid, strong base titrations are the easiest of the 3 types of titrations. Okay? Because you don't have to worry about the salt you're making. Okay? Enjoy that while it lasts. Okay? All we need to worry about is the fact that we still have some HCl left. So I want to get the pH. pH is the negative log of the H plus ion concentration. That is not a concentration. It's moles. We need to turn this back into a concentration before we can plug it into the pH equation and solve for the pH. So we need to divide by the new volume. We had 25 mils of solution in here to start. We added 5 more mils. That's 30 mils. So we need to divide this by the new volume of 0.0300 liters. That is a 0.0667. I'm going to go with 3 sig figs. Yeah, I'm feeling 3 sig figs. 0.0667 molar solution. We plug that in, negative log of 0.0667. And that's a pH of 1.18. So again, if we're making a pH curve now, after we've added 5 mils of stuff, the pH has barely increased. Goes from 1 to 1.18. Barely increased. Barely. Okay? Let's add some more, right? Let's do another point. Maybe let's add, I don't know, let's add 18 mils of sodium hydroxide. So this is wonderful. I love having a whiteboard. I'm sorry for you all at home. Point C, I want the pH after 18.0 milliliters of the 0.1 molar sodium hydroxide is added. So I get to reload very quickly because I got this beautiful BAA table. The reaction is the same. The original amount before we add any titrant of the HCl is the same. What's going to be different? We're going to have a different amount of sodium hydroxide we've added now. We added 18 mils of this 0.1 molar. So I want you to get the moles of that. Then I want you to see if you can fill out the bottom column. see if you can get the new concentration, see if you can get the pH. So go ahead. Okay, again, you're gonna take you longer to rewrite all this because you don't have a whiteboard. Okay, but see if you can't fill out the rest of the table. Okay, now with the 18 mil addition, we're still not at the equivalence point. Equivalence point is 25 mils. We're only at an 18. Okay, so we're not at the equivalence point yet. Go ahead. All right. So to get this, we need to multiply the concentration times the volume in liters. So that's going to be 0.0018 moles. I have enough acid to cover the base, so no base left. We're going to subtract. So that's now 0.00070 moles of acid. We're going to turn that into 0.0018 moles of a neutral salt. For now, enjoy that, because in just a few minutes, when we do the other kinds of titrations, that's not going to be a neutral salt. It's going to be rough. Okay. Not too bad as long as you're not at the equivalence point. Then it's rough. Anyway, so we're going to divide by the new volume, 25 mils plus 18 mils. So 25 plus 18, we have 43 mils. So we're going to divide by 0.04300 liters. And that's going to be a concentration of H plus. So that's an H plus ion concentration of 0.0163. Might be down to 2 sig figs here, right? Because of the addition subtraction sig fig rules. I'll give you some leeway if you give me 2 or 3, especially in a problem like this, especially when you're taking a logarithm. I'll take 2 or 3 sig figs. I'll take 2 or 3 places past the decimal in the pH. Anyway, so now pH equals the negative log of that. So negative log, and I'm going to say there's 2 sig figs, so 1.79. 1.79. It's just barely, and if you look at a pH curve, it barely changes, and all of a sudden, boom, right? So you got to remember, we added 18 mils. The equivalence point is at 25 mils. We're only 7 mils away from the equivalence point, but then it shoots up right at the equivalence point. So let's do one more point before the equivalence point. Why not? Let's get really close to that equivalence point. Let's add maybe 23 mils of titrate. So what's the pH after? I know, it's so great to have a whiteboard. What's the pH after 23.00 mils of the 0.1 molar sodium hydroxide is added? Go ahead. You got this. Right. So we multiply the concentration times the volume of the titrant in liters. So 0.1 times 0.023 is 0.0023. We look, we still have enough acid in there, but to cover it, so no base left. But now it's down to 0.0002 moles. We will have made this much neutral salt, but since it's a neutral salt, it doesn't matter. Divide by the new volume. 25 plus 23 is 48. So we're dividing by 0.0480 liters. And that's a concentration of 0.0042 molar. So pH equals negative log of that. And we finally, the pH is climbing now. We're up to 2.38. So right before the equivalence point, there's 25. We're up to like 2.38 here. And now I want to do the equivalence point. So let's do the equivalence point. We're going to do the equivalence point, then we're going to do a point after the equivalence point. So E. I want the pH after 25 mils of the 0.1 molar sodium hydroxide has been added. And we'll do this one together. Hang in there, because this one is fast. Watch. What happens at the equivalence point? The equivalence point is when the amount of acid in there and the amount of base being added are equivalent. So if we think about it, like obviously if I take 0.100 moles per liter and I multiply it by 0.02500 liters, I get 0.00250 moles of the sodium hydroxide. The amount of acid and base are the same. So what happens? Well, I have no base left, but I have no acid left, and it's all been turned into this salt. Now, this one is nice because the salt is a neutral salt. So what do I have? I have a neutral salt in water, and that's it. So what's the pH of a neutral salt in pure water? Well, the pH is 7, right? So that's why the equivalence point of a strong acid, strong base titration has a neutral pH. Because at the equivalence point of a strong acid, strong base titration, the two have neutralized each other, and the only thing left is a neutral salt and water. Now, when we do a weak strong titration, the salt is not neutral, and the pH is not 7. Okay, so that's coming, but hopefully you can appreciate that. I want to do one more point in a strong acid, strong base titration. I want to go past the equivalence point. So what happens if we keep adding titrant? So point F, I would like the pH after, I don't know, how about 30 mils of the titrant has been added. So I'd like you to try to fill in the BAA table, and then we'll talk. So see if you can't fill in the rest of that BAA table, and then we'll talk about how to get the pHs again. So I've added 30 mils now. Get the mole, think about it. Okay. So when I add 30 mils of a 0.1 molar solution, that's 0.00300 moles. I do not have enough acid to cover it. So now, since I'm past the equivalence point, I've consumed all the acid, and I'm actually going to have sodium hydroxide left over. And then all of that will have been turned into a neutral salt. Here's what's going on. When you get past the equivalence point, so we're at 30 mils now, the titrant is in excess. So what do I have? I have sodium hydroxide left over. I need to turn this into a concentration, but then that's the concentration of a strong base. I'm going to get the POH, and then I can get the pH. So what do I need to do? I need to turn this into a concentration by dividing by the new volume. 25 mils plus 30 mils, that's 55 mils. So we're going to divide by 0.055 liters. That is 0.0091 molar hydroxide ions. And now the POH equals the negative log of that. That's a POH of 2.04. And then 14 minus that, so 14 minus 2.04, that's a pH of 11.96. And now you can see the pH, would absolutely skyrocket. What it actually does is it skyrockets and then starts to level off again. So these BAA tables, they're pretty darn handy, right? We use the BAA tables for the buffers, and then we use a BAA table for titrations. Okay. Now this is the easiest kind of titration because it's strong.